All right, so we're going to go over 3 ways to get a total if we don't know what the total is. Now, we're going to kind of write down an outline first, and then we'll kind of go back and fill it in with an example. All right? Now, this counting principle, let me ask you this. You might not know this if you've never been around little kids. And I will tell you this. If I've got to take 5 kids to lunch, I'm the kindergarten teacher, and you know, we're in the cohort, I've only got 5 kids in there, and I've got to line them up for lunch. Do you think it matters the order that I line those kids up in to go to lunch? You ever taught 5-year-olds? Do you think they care what order they're in? Oh yeah, they really care what. Now they're going to the same place, like a half a second apart, do you understand? But being first is really important when you're 5. Now, but you might not know that if you've never been around kindergartners. So on a test, it's going to be real important if you know if order matters or not. So realize on a test, you can walk up to this table and ask me, does order matter on number 4? I'll either do this or I'll do this. Okay? Because you might not know what 5-year-olds do. All right? So what I need you to know is on the counting principle, order matters. I need you to know on permutation, order matters, whatever that is, and on combinations, order does not matter. Okay? So we're going to talk about this in a minute, but when you read the word problems, one of the first things you're going to ask yourself is, does order matter? Now, if the answer is no, what's the only one that you can grab when order does not matter? We don't know what this is, but you're going to grab it. Combinations. All right? If order does matter, this one's out. You cannot pick that one. So now you've narrowed it down to either permutations or the counting principle. Okay? Now, the counting principle, the nice thing about the counting principle is this. It can be used with or without replacement. All right, so whether I'm keeping things or putting them back, I'm going to be able to use the counting principle. Now, the permutations formula that we're going to be using can only be used without replacement. So if replacement is allowed, we're up here. Is everybody with me? If I don't have replacement, then I can either do this one or that one, kind of my choice. The other thing with what we're going to be doing is the counting principle allows for special conditions. And the permutations formula we're going to be going over does not. Right? So in your notes, you've got 3 ways to get a total. You've got the counting principle, you've got permutations, and you've got combinations. Remind me one more time, if order does not matter, what are you going to have to grab? Combinations. Okay? Now, let me kind of show you here's my question. When you graduate from college, all right, and you get your job, what usually happens is you probably have to go shopping for some clothes. Okay? Because you can't wear your shorts, you can't wear your sweats, you can't wear your pajama pants, you can't wear all that to the office. But you're poor. Okay? So what happens is this, when you take a professional protocol class, one of the things that they tell you is this, you really, at the beginning when you got a professional job, you really need to buy a few pieces of quality clothing that all match. And it's based on the counting principle. All right, so let me show you what I'm talking about. Now, the counting principle basically says this. If the first event occurs in ways, and the second event occurs M ways. They both occur, they occur together, let's phrase it that way. They occur together M times N ways. In other words, I'm just going to multiply the number of ways that each event can occur, and that tells me the total. All right. Now, let me show you what I'm talking about. Suppose, like I said, you graduate college. All right. And here's what you do. You go to the store and you buy 2 pair of pants, and you buy 3 shirts, tops, whatever you want to say. So you've got 2 really nice pairs of slacks that, you know, didn't cost $5 each, okay? And you got 3 nice shirts or tops, depending on male or female, right? And what I want to know, though, is that every pair of pants matches what? Every shirt. So what I want to know is how many outfits can you make? So how many outfits are possible? Now, we're going to define an outfit as a pair of pants and a shirt. We're not going half naked to the office. Okay. Okay. We want to get fired on day 2. All right. We're not zooming like that cute commercial where the guy comes out and makes you zooming. All right. Now, how many pairs of pants? When you go in your closet to pick, how many choices do you have for your pants? How many? 2. When you go to pick your shirt, how many choices do you have? 3. So according to this counting principle, what do I do with these 2 numbers? I multiply them, and I get how many outfits can I make? 6. So I bought 5 pieces of clothes, and I can have 6 outfits. So I can go a whole week without wearing the same thing twice to work. All right, now, maybe I save up my money and work a couple of months. All right, here's where the power of the counting principle comes in. I save up a couple of months and I go do this. The weather's turning cooler. So I go and now I buy 2 jackets. Blazers, cardigan, something. Are you with me? So I've got 2 jackets. Now what I want to know is how many outfits can I make? Well, now think about it. If I define an outfit as a pair of pants and a shirt and a jacket, and again, everything matches. Maybe I'm going with like a brown, cream colored tan thing, or maybe I'm going with, maybe I like the little colors, so maybe I'm going with black and white and red or blue. You're saying like everything matches though. When I go in to pick up my pants, I still have how many choices? 2. When I go to pick out my shirt, how many choices do I have? 3. When I go to pick out my jacket, how many choices do I have? 2. Now, what's the counting principle say I do with those numbers? When I multiply them? Now, how many outfits do I have? I have 12. So, work week, I can go 2.5 weeks now, but I didn't buy double the outfits. You with me? So I jumped from 6 to 12 by only buying how many things? Now, and think about the common sense. If you leave the jacket off sometimes, wouldn't you really have 18 different outfits? Only by buying 1. 2 pieces of clothing. So that's why, I mean, the fuchsia jumpsuit is lovely, but let's not spend our money on that, okay? So that's the reason they tell you to find a few pieces of quality clothing and make sure they all match. Because then you don't spend nearly as much money and you can wear, you know, you can go, if it's 18, I mean, that's more than 3 weeks that I can go to work and I don't have exactly the same thing on any 2 days, okay? So that's what the counting principle does for me. All right, now let me show you another one, the counting principle. Let's go back to lining those kids up. All right, so we had 5 kids and we're gonna line them up. All right, so how many ways can you line up 5 children for lunch? So we're gonna pretend like you don't have to eat in your room, which bless their baby hearts, they'll have to do right now, but okay. All right. Now, do you understand it's like there are 5 slots at the door? So when I go pick the first kid, how many choices do I have? 5. All right, maybe Stephen's being extra good, so he goes to the door. All right. Now, when I go back, how many choices do I have for number 2? 4. So maybe Faith is to go next. All right. So when I go back to pick it, what's my choice now? How many? 3. All right, maybe Annika gets to go. All right, then I go, how many choices do I have? 2. So Nadia gets to go to the door. Now, when I come back, how many choices do I have? 1. I like to leave that kid behind, but you go to jail. You with me? So I got to take the kid to lunch. Okay? So what's the counting principle say I do with those numbers? I multiply them. So you got your calculator. How many different ways can you line up 5 children to go to lunch? 120 different ways. That's why you're exhausted when you're in the kindergarten. All right. So go back to my original question about your PIN code with your debit card. I know what the number on top was, right? How many PIN codes did I have? I had how many? 1. But I didn't know how many total PIN cards there are. Now, how many digits does your PIN code have in it? 4. How many choices, when you go to punch the number, the PIN code, how many choices are there on that panel for you? 10. Now, is this one going to be 9? Do you only have 9 choices? I still have what? 10, because you can repeat numbers in a debit, can't you? And then I have how many choices? 10. How many choices? 10. So what's the calculus say I do with that? Multiply. So what's my total on the bottom? 10,000. So he's got or she's got a 1 out of 10,000 chance of putting my debit card in there the first time, punching it in and getting it right. Now, hopefully you know this. That's the reason you don't have unlimited attempts. If you had a smart, persistent thief that kept track, eventually they would get it what? Right. So most institutions on the 3rd time, they freeze your account. So then you have to go into the bank with an ID to get that account unlocked. Okay, so don't just keep punching in if you can't remember what your PIN code is. That also happens online a lot of times now. You're not with your password or something, it'll lock you out because it doesn't want somebody hacking it. All right. Now let's do one that's a little more fun, and then we'll talk about the others. What if you're making a secret code? Okay. And on this secret code, it has 4 single-digit numbers. I'm talking like 0 through 9, followed by, let's say 3 letters of the alphabet. So I'm talking like A through Z. All right, but there's some special conditions on this code. The first 2 numbers must be even. The first letter, for whatever reason, cannot be Z. And no repetition is allowed anywhere. So once you use a number or a letter, you can't use it anymore. So what I want to know is how many codes are possible? How many codes are possible? Now, if you've got a secret code, does order matter? Yes. So what am I not going to be able to use? This thing called what in a minute? Combinations is out. Okay. Now I've narrowed it down to either this thing called the counting principle or permutations. All right. No repetition. So far I'm good. Why am I going to have to use the counting principle? Because I've got what? Special conditions. I got these special conditions like the thing's got to be even, or I can't use Z or anything like that. So I'm thinking through what are my options here. Now, if you're just organized and you view everything kind of one blank at a time, it's not hard. You just have to take care. I've got 4 single-digit numbers. Now, I have to write notes to myself because I'm old and brain cells are done. All right, so those are numbers. All right. Then I have how many letters? 3. So again, I'm just writing notes to myself. You might not have to do this. I just find it helps me focus. Now, what do I know about the first 2 numbers? They have to be what? Even. So I'm going to remind myself, that one's got to be even, and that one's got to be even. What does it say anything special about the letters? The first letter, what? Not Z. So that's just GAN. You don't have to do it that way. That's just the way I help remind myself and how I get organized. All right. When I go to pick this first number, it's got to be even. So how many choices do I have? If I'm using the numbers 0 to 9. 5. Why 5? 0 is even what? 2 is even, 4 is even, 6 is even, and what? 8's even. Now, some people like when I put a 5 there. I'm not saying 5 is even. I'm saying there are 5 different even numbers from which to choose. Everybody okay? All right. Am I going to put a 5 in this one? Why? Because I can't repeat. So I've already used an even number. So how many choices am I going to have with this second number? 4. Everybody okay with that? Now, does this third number have to be even? No. Now, how many numbers were there originally? 0 to 9 is how many numbers? 10. Do I put 10 in the blank though? Why? Because I've used how many? 2. Which means how many choices do I have now for this number? 8. All right, same thing on this one. Doesn't have to be even. So there are 10 numbers, but how many have I used? 3. So how many choices do I have on this one? Yeah, good. Do those numbers make sense in those blanks? Okay? Now, when I go here, I can use any letter except I can't use what? Z. So how many choices do I have for my letter? How many letters in the alphabet? 26. How many choices do I have here then? 25. Now, I want you to think about the next blank for a second and I'll ask you. Is that 24? What number goes in that blank?
25.
Why 25? Because Z's back. I mean, there are 26 letters and I used 1 here. Is everybody with me? So I might have used V, but then Z gets thrown back in. So don't just start getting in the habit of taking the numbers down every time. So here there was nothing special. So again, there were 26 letters and I used how many? 1. What goes in this blank? Everybody see why it's 24? Because there were 26 letters and how many have I used? 2, which left me 24. What's the counting principle say I did with all those numbers? All right, so you find me how many codes you can make. Did you get a 1, 6, 8, and then a bunch of zeros? How many zeros did y'all get? Is it 5? So let's make sure we understand what number that is. We're understanding that 16 million what? 800,000. This counting principle things get really big really fast. But do you understand with the counting principle, you're kind of drawing blanks and seeing how many choices you have for each blank. And as long as you keep everything separated, life is great. All right, let's go back and look at the other two options then. Now, before we do the other two options, take your calculators out for a minute. I need to explain, because we're going to do something, I need to explain this symbol to you. All right, n, that's not an excited n, okay? That's n factorial. All right, so what it means is this. If you have like a 5 factorial, that means 5 times 4 times 3 times 2 times 1. That means you start at this number and you go down by ones until you get to 1 and you multiply them up, which ends up being 20 times 6 is 120. So what is 3 factorial going to equal? Everybody see why it's 6? Because it's what? 3 times 2 times 1. Now, there's going to be a formula for permutations and a formula for combinations, and both of them have this factorial symbol. All right? They're in your books. Let's see where they put them in your books. The permutation one's on page 171. And the combinations is on page 172. So I'm going to write the formulas down, and then we're going to use them. All right. So for permutations, they're going to put it this way. They're going to say P, and they're going to have a little N here and an R here. Now, what does N stand for? The whole semester, I told you. Your total. So that N is going to be your total. This R is how many you're selecting. How many you select. Okay? Now, if you look on page 171, they've got n factorial over n minus r in a parenthesis factorial. Okay? Now, combinations, all right, has a C with an N and an R. And again, what's N going to stand for? What's it always stand for? Total. And R is still going to be how many you're selecting. The formula is almost identical with one extra little thing. It's got an N factorial on the top. It's got an N minus R and a parenthesis factorial on the bottom. But right next to that, it's got another R factorial. Now, let me show you what I'm talking about. All right, so you write those formulas down, and then we're going to go work some problems with them. All right, suppose you have a tribe or club. Suppose there are, just make the number smaller for quick. Suppose there are 100 members in your club or tribe. Okay? And you need a committee. Can we still have phones? Of 8 people. How many committees can you make? How many committees are possible? In other words, how many different 8-person committees could you make? Okay? Now, I have a question. When you're putting people on a committee, does order matter? Does it matter if I pick Joe, Mary, and Sam, or Sam, Mary, and Joe? Does order on a committee matter? No. So if order does not matter, what am I going to have to do? This thing called what? Combinations. Okay. Now, N is my total. And we said R is how many we're selecting, right? Number you pick, number you select. What's my total in this problem? There, how many to pick from? 100. But how many am I picking? I'm not picking all 100. I'm only picking how many? 8. So do you understand that my N is 100 and my R is 8? Now, what's going to be on the top? 100 or 8 factorial? What's on the top? What's my formula? Isn't it N factorial over what? N minus R in a parenthesis factorial. Isn't that my formula for combinations? So what's on the top? 100 what? Factorial. Right on the bottom, I've got 100 minus 8 in a parenthesis what? Factorial. And then I've got an 8 factorial. So does everybody understand how I plug those numbers in? I plug in 100 for N and 8 for R. Now, what do you always do first? In order of operations. Don't you do parentheses? All right, 100 factorial. What's 100 minus 8? You got 92? Now, let me show you something. I'm going to do something small and then come back to this. If I had 40 factorial over 37 factorial, wouldn't 40 factorial mean 40 times 39 times 38 times 37, if I could write, times 36 times 35, all the way down to 1, right? What does 37 factorial mean? 37 times 36 times 35, all the way down to what? 1. What's going to happen to the 37s and the 36s and the 35s and the 12s? And what's going to happen to all those? They're going to what? They're going to divide out. So rather than writing it like that, does this make sense to you? 40 times 39 times 38. Why am I going to write 37 factorial instead of writing it all out? Because what's on the bottom? 37 what? Factorial. So do you understand I'm not canceling out, I'm not dividing out one number, I'm dividing out what? A bunch of numbers. But isn't that way quicker than doing all that? So do you understand right here, I'm going to go 100 times what? 99 times 98 times 97 times 96 times 95 times 94 times 93 times, what am I going to stop with?
92.
I'm going to stop with 92 factorial. Why? Because on the bottom down here, what do I have? I have what? 92 what? Factorial. Now, what does 8 factorial mean? 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Everybody see where I got that? So do you understand that those 92 factorial are going to divide out? So they go out. So get me your answer. Let me show you something with your calculator. And again, if it throws it in scientific notation and that freaks you out, just put things in a parenthesis. All right, did you get a huge number? All right, here's what I got on my machine. Did you get 1.860878943E11? Now, what does that mean? That means, this is scientific notation, so that means that decimals are supposed to be 11 places which way? To the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Everybody with me? What I have to do? 2 more zeros. Everybody okay? That's a lot of committees you can have. Like 186 billion, 87 million, 194. Everybody think you have a lot of committees. Now, let me show you something on your machine. So let's do one more real quick. Let's go back to the kids lining up. Is everybody with me? All right. If the kids line up, do we say order matters? It does, doesn't it? All right. So if order matters, I've narrowed it down to either permutations or the what? Counting principle. Do we agree? All right. Am I going to repeat the same kid at the door more than one time? I'm not. Are any special conditions like Laura can't go first? So I did it this way before, but you see that I could do it this way if I wanted to? Because order matters and what? I'm not replacing anybody. So I could work it this way, all right? So if I work it that way, what's going to be my n? How many kids are there total? Do you remember? There were how many? Weren't there 5? And how many were we taking to lunch? Were we taking all 5 of them to lunch? So if I use this formula, what's on the top? What's my n? Don't I have 5 factorial? On the bottom, I have 5 minus what? 5 in a parenthesis factorial. Everybody with me? So I've got 5 factorial on top of what? 0 factorial. Now, by definition, 0 factorial is 1. So I've got 5 factorial on top of 1, which is just 5 what? Factorials. Everybody with me? Now, what does 5 factorial mean? You told me a second ago it meant what? 5 times 4 times 3 times 2 times 1, which is, isn't that what we got the first time when we used the counting principle? Now, let me show you something about your machines. Your machines will do all of this for you. All right, here's what I want you to do. I want you to find first this factorial key in case you need it. But what you're going to have to do is type in your number first. So type in 5. Now, to get to the factorial key, here's where I need you to go. All right. I need you to go to the math key. Does everybody see the math key? It's like 2 below your second. Everybody find the math key? Hit the math key. Now at the top it says math, NUM, CPX, and PRB. What do you think PRB stands for? What? Probability. So hit PRB. So right arrow over to PRB. Now do you see number 4 on your menu? It's number 4 on mine. There should be a factorial menu. If I scroll down and hit number 4 on mine for factorial, on my machine it now says 5 factorial. And when I hit enter, 120 comes up. Is everybody okay? Now, look what happens if you try to do 100 factorial. Try 100 factorial with your machine. So 100, you go to math, you go over to probability, and you go down to factorial. What happens when you do that? You get an error message? The reason you get an error message is this machine doesn't have enough memory to do that. 100 times 99 times too big, it can't do it. All right? So that was kind of the reason for learning to divide some things out. But go back to your math, go back to second mode and quit. Go back to your math menu for a second. Go over to probability and look at numbers 2 and 3. What do they say? In PR and what? In CR. Is everybody with me? These two formulas are built into your machines. So what I want to do is I want to go back to this combinations problem and work it with your machine. All right, so we set it up like this. Now, here's what you're going to have to remember to do, though. Go back to your regular cleared screen. You've got to type in your N before you go to your math key. So I'm going to type in 100. Then I'm going to go get this C. Now, where was it? I went to what? Math. And then I went over to probabilities. Everybody with me? Now, am I wanting the C one or the P one on this one? I'm wanting the what? Did it say C? So make sure you pick the right one. And on your machine, it should say 100, and then it says NCR, and it's blinking. It's waiting for you now to tell it R. So what are you going to hit? 8, and then hit enter. And there comes that same number. All right. Now, let's go back and work the one with the kids using the machine. Now, wasn't that a permutations one? So I'm doing 5. I go to the math key. I go over to probability. Now I come down to NPR, and then I want to take all 5 with me. And I hit enter. And 120 comes up. Okay? So your machines will do it. Now, sometimes things are named properly and sometimes things are not named properly. And here's what I mean. When I drive up to Wendy's or McDonald's and I get a combo, it is literally a combo. It's a combination. That's why it's called a combo. It doesn't matter whether I tell them about the hamburger or the fries or the drink first. Is everybody with me? It all gets in the bag. So a combo, when I drive up to McDonald's or Wendy's, is properly named. Okay? But y'all are so young, you probably never had a lock on your locker. But you maybe have a lock on your bike. Those are called combination locks with the dials. Does the order that you put the numbers matter? Yes, it is misnamed. Even though it's called a combinations lock, it's not a combination lock because order what? Matters. Okay? So we got to be real careful about things. Now, let me show you this. Now, I want to make sure we're clear. Let me see which one's on the screen. On your homework, sometimes it's going to be a little confusing maybe to you about does order matter. So let's make sure we're clear about something. If I drive for UPS, we're going to talk about routes. Routes are the actual path my truck takes. If I've got to deliver a package in Clinton, Madison, Byram, and then Canton, does the order I deliver them change my route, like the path my truck goes? Yes. You know, you don't want to be delivering it to Clinton and then to Canton and then back to Byram and then up to Madison. You see what I'm saying? Like that would waste so much gas. So when it says route, again, order what? Matters. And so homework may be a little confusing occasionally when, you know, I don't know if order matters or not. But on a test, you can come ask me, does order matter? I'm going to go this way or what? Or this way. So when you're looking at the word problems, the first thing you better ask yourself is, does order matter? Does order matter? What if the answer is, does order matter? And the answer is no. Order does not matter. What are you automatically going to have to pick from your choices? You're going to pick combinations. Now, if the answer is yes, then you're going to have to answer the second question. Is repetition allowed? Now, you're either gonna get again, no or what? Or yes. If the answer is no, do you understand I can use either of these? No and no. That'd be my choice, so to speak. But if repetition is allowed, which one am I going to have to use now? I'm going to have to use this counting principle. What if you have special conditions? You're going to have to use this what? Counting principle. So do you understand that if order matters and you're not sure, which one of these two should you grab? Permutations or the counting principle? Always grab the counting principle if you're unsure if order matters, because this works every time this was. So if you get confused about, do I use the counting principle or permutations, which one are you going to grab? Counting principle. The only advantage of permutations is it's programmed in your machine. Okay? Now, let me make sure we're clear about something. We're going to talk about this a lot more later. Suppose I decide, for some bizarre reason, because my brain takes a break, that I want to buy a lottery ticket. Now, I want to make sure we're clear about something. Sometimes order matters in a lottery and sometimes it doesn't. All right? Because I've only got a few minutes. Let's suppose order matters in my lottery ticket. Because when order matters, you make more money. Now, a lot of times in a lot of states, you can have something called like 5-number lotto. Now, what 5-number lotto means is literally I'm choosing 5 numbers. And each of the numbers is a double digit. So in other words, I can choose 00 to 99. Is everybody with me? So I go in that little convenience store or whatever, and I want to buy a 5-number lotto ticket for $10 or $5 or $2, whatever they cost. I don't even know. All right. And I get to either let the computer generate, or I get to pick. You know, maybe the first is my birth, and maybe the second's my anniversary. You know, I get to pick the numbers. How many choices do I have with this first number? From 0 to 99. How many choices is that? That's 100 choices. Now, you can repeat numbers. So when I go pick this number, how many choices will I have? How many? You tell me. 100. What about this one? Another what? 100. What about this one? Another 100. And what about this one? Another what? 100. What's the counting principle say I do with those? Of what? So what's your chance of winning that week? About how many tickets? How many are there? 10 what? Billion. Don't you feel lucky? You got a 1 out of 10 billion chance of winning. Well, I'll go buy 10 tickets. Ooh. Now you got a 10 out of what? 10 billion. I want you to think this through. It's not like buying a ticket for the raffle for the football team. This isn't buying a ticket for the St. Jude house. So do you understand, if I work for Lotto, if I work for the lottery or whoever this is, there are 10 billion tickets. What if I sell 1 million tickets? What if I sell 1 million tickets at $5 each? How much money comes in that week? 5 what? 5 million. I sold 1 million tickets. Now how many tickets are there? 10 what? Billion. So how many tickets didn't get sold? 9 billion 999 what? 995 what? 999 million tickets didn't get sold. So when the computer spits out that winning number, is it likely that somebody has it or nobody has it? Nobody has that number. What happens to that $5 million? Who gets it? They do. So now they throw another $500,000 in the pot. So next week the pot's got Maybe the pot's like $1 million, the next week it's like $1.5 million. What happens to their ticket sales when the pot goes up? It goes up. Maybe next week they sell 2 million tickets at $5 a piece. So now $10 million comes in. But again, if they sell 2 million tickets, do you understand that means 998 million didn't get sold? So again, when the number's drawn, who probably wins? Nobody. You do understand people, they sell the same ticket more than once. Someone's coming with the same number, they'll sell it to you. You do understand that the first thing that happens is, if you win, what's the first thing that happens? What comes out of that money before they ever hand it to you? Tax. How much thing comes out of that tax? Now, they've done research. I need you to understand that people that win these giant lotteries, in 5 to 7 years, the majority of them are poorer than before they won. Why? I mean, no offense, but financial geniuses are not buying the tickets. Do you see what I'm saying? Because if you buy the house, you're going to pay the property tax next year. So I'm saying, if you want a thrilling 4 seconds, knock yourself out. Okay, and once again, it's a thrilling 4 seconds. All right? Where's your homework going to be? Move. Go to the easy. And be looking for another video to watch. So watch those deadlines on those videos.